Okay, I'm going to pick up where I left off on the previous video. I had to stop because, in fact, I noticed I made a mistake here. This permutation is not correct. Let me be a little more careful here. Oops, turn the color. And we have, what's the permutation here? 1 goes to 3. 3 doesn't go to anything. Okay, and let's see what 3 goes to. 3 goes to 2 here, and 2 goes to 4. Let's see where 4 goes. 4 goes to 1. All right, so that was an incorrect permutation. It turns out I went on for a while and discovered my mistake later on. So that's what happens if you do make a mistake. You'll probably find out that you'll get the same permutation twice, which means that you made a mistake somewhere. So you'll just have to go back. All right then, let's see what else we can do here. We have 1, 2, 3, 4, 5, 6 cosets. We're looking for 8 cosets. We want to include all the possible permutations. So in order to find another coset, we need to find a permutation that we haven't done so far. Now, we've done exercises before about the types of permutations within S4. For instance, we have 2 cycles, or 3 cycles, or 4 cycles, or products of 2 cycles. All right. If we look at the permutations we have so far, we have a bunch of 2 cycles. We have a bunch of 3 cycles. We have a lot of 4 cycles. We don't have that many pairs of 2 cycles. So let's go and see what we can do about that. All right, here we have a two cycle 1, 4, 2, 3. We can get another pair of 2 cycles. Let's try 1, 2, 3, 4. Okay. All right, so if I take 1, 2, 3, 4, 3, 4 times 1, and then 1, 2, 3, 4 times 1, 2, 3, and then 1, 2, 3, 4 times 1, 3, 2. What do I get? Well, first one is going to be 1, 2, 3, 4. Second one is going to be 1 goes to 2, 2 goes back to 1, so 1 doesn't go to anything. 2 goes to 3, 3 goes to 4, so here I'm going to get 2, 4. And I'm betting that it's going to go to 3, but let's check. Here 4 doesn't go to anything, 4 goes to 3, yep, 4 goes to 3. Let's check what 3 goes to. 3 goes to 1, 1 goes to 2, so we get 3 going back to 2, and we're good. All right, let's look at the last one here. 1 goes to 3, 3 goes to 4, so that means 1 goes to 4. Okay, let's see what 4 goes to. 4 goes to 3. Let's see what 3 goes to. 3 goes to 2, 2 goes to 1. All right. Okay. Let's see if we're missing anything else. Okay. Here we had 1, 4, 2, 3. Here we had 1, 2, 3, 4. Looks like we're missing another pair of 2 cycles. We could do 1, 3, 2, 4. Okay, so that would be 1, 3, 2, 4 times 1. When you do it, you don't have to rewrite this all the way out again. I think as you get better with multiplying permutations, you don't need to rewrite. However, notice that it is easy to make a mistake, and I suggest you do this in pencil, because when I did this, I made a couple of mistakes. And it's better to go back and correct than to redo the whole thing. All right, so the first one is going to be 1, 3, 2, 4. Second one is going to be, let's see, 1 goes to 2, 2 goes to 4, so I'm going to have 1, 4. And I'm betting these are going to be 3 cycles, judging from the pattern, so let's see if that works out. 4 goes to 2, looks like that's this one here. And 2 goes to 3, 3 goes to 1, so it closes. Let's check that 3 goes to 3, 3 goes to 1, 1 goes to 3, so we're good there. Okay, and let's see, 1 goes to 3, 3 goes to 1, so 1 doesn't go to anything. 2 goes to 1, 1 goes to 3. 3 goes to 2, 2 goes to 4. 4 goes to 2, we're done. Okay. All right, so notice what we have. We have 8 cosets. They're disjoint. Okay. They form a partition of S4. Okay. So they're actually equivalent classes. And they all have 3 elements. And that's the same as the original subgroup. Okay. So notice what we've done here. We've divided the group S4 into 8 sets. Let me get rid of this because I don't need this anymore. We've divided the individual group into 8 sets where each set has the same number of elements as the original subgroup. What can we conclude from that? The number of elements in the subgroup must divide the number of elements in the group. Okay. Okay. In order to make the partition work. Think about it. It's just a counting thing. Suppose you have 24 oranges and you want to divide equally among 4 people. Well, 4 must divide 24. You can't possibly divide 24 equally among 5 people. So in this case, when we want to divide the elements in a group into cosets, and each coset has the same number of elements, that means the number of elements in the coset must divide the number of elements of the group. Okay. So this is called Lagrange's theorem. And I'm not going to go any farther with this theorem except to say that it's an amazing result that the number of elements in any subgroup must divide the number of elements in the group it's taken from. Okay, so that's an important thing. Another important thing here is that I've shown the left cosets. The right cosets are different. In this case, our operation is not commutative, so we can't expect necessarily that the right cosets will be the same as the left cosets. Okay, so you'll have to finish this up. You'll have to find the right cosets. You can use the same method. You won't find the same cosets, but you can use the same method. You're going to have 8 cosets. Of course, the original coset will be the same. And it's possible that some of these cosets may be the same, but in general, the cosets will be different. Okay, so see where you can go with that. There's 2 other cosets problems as well that you're supposed to do. Let me see if I can find those. Not here. You should also do A and F. Let's take a look at those for a second. All right. And notice that A is in Z24. So that's a commutative group, so you're not going to have to worry about the difference between left and right cosets. And then you have D4 and S4. D4 is the dihedral group. That's the symmetries of the square. If you remember, that has 8 elements in it. So you can figure out how many cosets that's going to have. 8 elements in 24 elements. Okay, so have fun with that.